lectures we've seen isolated magnetic moments, what their energy is, how do they respond to magnetic field gradients. There are forces acting on dipoles, and then we've also seen how torques act on dipoles, and the dipole magnetic moment was related to the angular momentum. The angular momentum could have an orbital origin, it could have a spin origin. So this is what we've covered so far. Now what we would like to introduce is how do magnetic moments interact? Because in order to study magnetism in the solid state, we have a large number of moments. Each ion could be a moment. Each electron, a conduction electron, could be a moment. Now how do these electrons, these particles interact with one another? So first we've seen isolated magnetic moments. Now we would like to switch on interactions and what are the different kinds of interactions. Now we know that we have a spin. Just to give you an overview, this spin can interact with an external magnetic field. So this is an external magnetic field. We know that this spin interacts. There could be a torque acting on it. If this field is inhomogeneous, there could be a force acting on it. And the effect of this field is to align the spins. And the energy of this spin inside the field is minus mu dot B. So this interaction between the spin and an external field is generally called the Zeeman interaction. Okay. Now we could have an ensemble of spins, a large number of spins, a certain concentration of them. Now these spins can interact amongst themselves. Now there are different mechanisms of this interaction. So the spins could interact within their own manifold. They could interact through the dipolar interaction. They could interact through the exchange interaction. The exchange interaction could be of different kinds. It could be direct exchange, indirect exchange. You could talk about hyperfine interactions, all of these. So spins are interacting amongst themselves as well. In fact, this is one of the most important interactions which gives rise to ferromagnetism or antiferromagnetism or ferrimagnetism. But then you also have these spins inside a crystal structure. So you could have a crystal structure. The crystal structure, as you all know, is defined by a grid of points which is called a lattice. So you can have a lattice. And on each point you place a motif. You place a collection of atoms or ions or molecules and form the crystal structure. Now these spins can also interact with the lattice. And this interaction is called the spin-orbit interaction. So there are different degrees of freedom. There is an external magnetic field, there are spins, there is the lattice, and all three of them could interact with one another. There are additional degrees of freedom as well. For example, you can have a photon. Okay? There could be interaction between the spins and the photon, which gives rise to optomagnetic or magneto-optic effects. You could also have oscillations of this lattice. This lattice can oscillate in a quantized fashion. These quantized oscillations are called phonons. So there are different degrees of freedom, and the spins can interact with all of them. So the spins can interact amongst themselves, they can interact with the external magnetic field. This is generally the name given, the Zeeman effect, exchange interaction. The spins can interact with the lattice, spin orbit. The spins can interact with the photon, giving rise to magneto-optic or optomagnetic effects. Spins can interact with phonons, giving rise to magnetoacoustic effects, for example, or acoustomagnetic effects. So there are different degrees of freedom and they all interact with one another. So what we are interested right now in this part of the course is how the spins interact with one another. Now, one of the most obvious mechanisms is the dipolar interaction. Now, we know that two magnetic moments, they're just like tiny magnets, and magnets interact with one another. So, if you have two moments, mu1 and mu2, depending upon the relative orientation of these magnetic moments and the distance between these moments, there is a certain energy associated with this configuration. That energy, one learns from basic electromagnetism, is given by mu naught over 4 pi r cube, and then you have mu1 dotted with mu2 minus 3 over r square mu1 dotted with r1 multiplied with mu2 dotted with r2, where r1 and r2 are the position vectors of the two dipoles. So there is an interaction energy associated with these two magnets, these tiny magnets. Each one of them carries a magnetic moment, mu1 and mu2. Now this can be derived, and I'll put this as a homework problem in the second homework. This could be derived. So if the spins are parallel, mu1 and mu2 are parallel, the angle between them is 0, a certain configuration, a certain energy results. And if these spins are anti-parallel, another energy results. So depending upon the relative orientation or disposition of these magnetic moments, you could have different kinds of energies. You could assume that this magnetic moment is a tiny dipole which is creating a magnetic field, and then you place another dipole at this position, at the position of this magnetic field. Now, given E is equal to minus mu dot B, this can have a certain energy depending upon what the field direction is and what the magnetic moment's direction is. And this is what it all turns out to be. Now it seems that this is an important effect. However, if you plug in the values, you have two atomic magnetic moments. Suppose you have 1 angstrom apart, you plug in these values, you put in typical magnetic moments of the order of the Bohr magneton here, this energy turns out to be really small. Turns out to be 10 raised to the power minus 23 joules, which is about 0.1 milli-electron volt or 100 micro-electron volt. It's a really small energy. It corresponds to a temperature of about 1 Tesla. See, all energies can be related to temperatures through kBT. So this energy is really small. But you see that there is some kind of interaction even at room temperature. You have iron at room temperature at 300 kelvins. So this energy, this interaction between the spins cannot explain these strong effects. It's a very minute, it's a feeble effect. Dipolar interactions do exist, but they only play an important role at temperatures of the order of 1 Tesla or 1 Kelvin. Sorry. So they only play a significant role when the temperature is of the order of millikelvins or a few kelvins. At room temperature, the dipolar interactions are really small, if you talk about electrons. In NMR or other kind of spectroscopy, they can become important, but as a general rule of thumb, the dipolar interactions, even though they exist, it's a low temperature phenomenon because the energies involved are really small. So what is the major mechanism by which spins interact with one another? It's called the exchange interaction. Now we'll spend quite a few lectures on the exchange interaction because this is at the heart of magnetism. And if I would just like to sum up, the exchange interaction is simply an electrostatic effect. So if you know electrostatics, you can explain exchange interaction. It's an electrostatic effect, but to that you graft a concept that is borrowed from quantum mechanics, and that is the symmetrization postulate. And I'll explain what all of this means in a minute. So the exchange interaction is a result of electrostatic, Coulombic repulsion or attraction, Coulombic effects, and grafted on top of those Coulombic effects is the symmetrization postulate of quantum mechanics. So both of these effects combine to give you the exchange interaction. Now, one of the earliest marvels of quantum mechanics, which appeared in one of Heisenberg's papers from 1928, is the description of the helium atom. And this is what we're going to do right now. And the description of the helium atom will give us a good idea of how the exchange interaction arises. So we're going to reproduce some of Heisenberg's work from 1928. However, let me first of all give you a motivation for the symmetrization postulate. We all know the Schrödinger equation. The time-independent Schrödinger equation is simply this equation. This is the time-independent form of the Schrödinger equation. Now this does not include the spin, because the Schrödinger equation predated Dirac's derivation of his equation, which straightforwardly predicted the concept of spin. But even before Dirac, Pauli came up with an equation which is called the Pauli equation, which is an artificial grafting of the spin concept onto the Schrödinger equation. So if this is the electron's Hamiltonian, just the spatial part of the electron, what Pauli suggested is adding a spin Hamiltonian to the overall Hamiltonian, and this equation is generally referred to as the Pauli equation. So by brute force, a term can be added to the Hamiltonian, the overall Hamiltonian, which represents the spin. This is the time-independent Schrödinger equation. And it turns out that if you solve the Dirac equation and keep the lowest order terms, the Pauli equation pops out as a result. Now, let's look at this equation here. Now, in this equation, there is a spin-dependent Hamiltonian. The spin-dependent Hamiltonian, you must know by now, is given by some lambda g factor, mu b over h bar, s the angular momentum, say the spin, we're talking about the spin here, the spin angular momentum, and you take the dot product with some magnetic field. So this is the spin dependent Hamiltonian. Okay. Now you solve the Pauli equation, you find the eigens, you could find the eigenstates, you can find the eigenvalues. Now let's look at the electronic part of the Hamiltonian, and let's just consider a single atom, just one atom, an isolated atom. Now in that atom you have electrons. Each electron is a magnetic moment, has a spin. Now if I were to write the Hamiltonian, the electronic part of the Hamiltonian, the atomic number is Z, so there are Z protons inside the nucleus. Now the Hamiltonian, suppose I would just like to write a Hamiltonian for the ith electron. Okay. There are n electrons in here. The atomic number is Z. Since it's a neutral atom, there are Z protons and Z electrons, or n electrons. Now, for the ith electron, the Hamiltonian will be given by a kinetic energy, right? Where m is the mass of the electron, plus an electrostatic term. Now, that electrostatic term is the electrostatic interaction between the electron and the nucleus. The nucleus carries Z positive charges. So, you have Ze positive charges and one electron, we're considering just one electron, Ze squared 4 pi epsilon naught Ri, where Ri is the position of the electron inside the atom with respect to the origin, which is the center of the nucleus. What kind of sign should I put here? A negative sign, because there's attraction between the nucleus. Now, this is the Hamiltonian for an isolated electron, but that ith electron is talking to n minus 1 electrons. So this is the nuclear attraction, but that electron is experiencing electrostatic repulsion from all the other electrons as well. So there has to be a term has to be added to that effect. Now that term is going to be, if we talk about 2 electrons at a time, so that term is going to be E squared 4 pi epsilon naught, the distance between 2 electrons. Now you have an I electron and you have some other J electron. So the distance between those electrons is Rj minus Ri, the modulus of this, and then you sum up over all other electrons, J, all the J electrons where J is not equal to I. And what kind of sign should I put here? You have 2 negatively charged electrons, so they are repelling one another. Minus E and minus E will give you plus E square, okay? So you have a positive sign here. So this is the Hamiltonian for the ith electron. Okay, but you have a large number of electrons. So if you would like to write down the total Hamiltonian, the electronic Hamiltonian for this atom, what you will have is pi square over 2m, and you have sum over all the i's, plus or minus Z e square over 4 pi epsilon naught 1 over Ri, sum up over all the i's. Okay, because you have n electrons. This sum runs from 1 to Z, or the total number of electrons. Okay. Now you have this. Remember, is a pairwise term. This is a pairwise term. It involves 2 electrons at a time. So you would like to find out all the pairs inside the atom. Now, so which means you would like to have a term of this kind, plus E square over 4 pi epsilon naught. Let's figure out what do we have in this sum later, but you have 1 over Ri minus Rj, or Rj minus Ri, doesn't matter. Now, what would you like? You would like to sum up over all the i's and all the j's at the same time. But what you would like to do is, you would like to write something of this kind, I is less than j. Now what does I less than j mean? I less than j means, this summation means that you are summing up over all i's and all j's, but you're halving this. Why? Because if you sum up over all i's and all j's, then first electron, second electron, I is 1, j is 2, but then you have I is 2, j is 1. So it's the same pair, you're double counting the pair, each pair. So in order to reduce, or in order to circumvent this double counting, you have to reduce by half. This also means that j can take up values from 1 to capital Z, where Z is the total number of electrons, and I goes from 1 and is less than J. Now, you can suppose you have 3 electrons, 1, 2 and 3. So what you would like to do, you would like to form a sum of 1 over R12, which is this distance, plus 1 over R13, which is this distance, plus 1 over R23. Okay, so for 3 electrons, this is what your sum must contain. Now, if you look, the first index is always less than the second index. Okay, so this is what I've written over here. Or you could take all indices, so you could take R12, you could take R21, but then you need to half. Because 1 over R12 is the same as 1 over R21. Okay? So this means you take all i's and j's, but I is not equal to j, remember. Okay? So all 3 of these variants of the summation hold true. In short, this is the electronic part of the Hamiltonian. Now, if you would like to find out the eigenstates, you would like to diagonalize this Hamiltonian. Okay. Remember, in this Pauli equation, the spin part of the Hamiltonian commutes with the electronic part of the Hamiltonian. This is a spatial term, this is a spin term. So the wave function, which are eigenstates of this, will also be eigenstates of this. Okay, so the spin part and the electronic part, they seem to be totally independent here. Okay, until we introduce the symmetrization postulate. They are linked, but mathematically they are independent. So this is the electronic part of the Hamiltonian. Now, if you would like to solve this Hamiltonian, which means you would like to diagonalize this Hamiltonian and find the eigenstates, how do we do it? If the electrons were non-interacting, this term would vanish, this term would not exist. So this term represents the interaction, the Coulombic interaction between electrons. So this is an interaction term, and it must be included for magnetism to take roots. Okay? Now, if this term were absent, you would have independent electrons. And each electron will be defined by a wave function given by the atomic orbital. And then all the electrons will be independent of one another. However, now you have an interacting system. This term exists. So you would like to solve this Hamiltonian in the presence of this term. Now, I hope all of you know what a central potential is. A central potential is a potential which only depends upon R, which only depends upon the distance from the nucleus. It does not depend upon any angular coordinates. Now, if this term were missing, then you had a central potential. Okay, and central potentials are easy to solve. It's just like solving the hydrogen atom, only that you have Z protons inside the nucleus. So, without this term, you have a hydrogen-like atom, but with many electrons. But each electron is independent, and each electron is as if it were in a hydrogenic atom with Z protons. However, this term breaks the centrality of the potential. So what you would like to do is somehow you would like to write down this term in the following fashion. You would like to break up HE into 2 parts, into a 0th order part and a 1st order part. And the 0th order part should be given by a central potential. So what we would like to do is we would like to write the above Hamiltonian in the following fashion. Pi square over 2m minus Ze square over 4 pi epsilon naught. Remember, here we're talking about epsilon naught, even though it should really be epsilon, the permittivity of that atom, but let's forget about that for a minute. 1 over Ri. Now what we would like to do is the following. We would like to introduce a term E square over 4 pi epsilon naught I is less than j 1 over Ri minus Rj. I'd like to take the average of this. So what we would like to do, we decompose He into two parts. One is the 0th order part, which is given by this. So this is a term that will be introduced on our own. What this means is that the electron has a kinetic energy, it has a potential energy with respect to the nucleus, but then each electron, the ith electron, each electron is seeing an average field created by all the other electrons. Okay, so this is an average field created by all the other electrons. So instead of having a pairwise interaction, you reduce that pairwise interaction to an average field. And that average field has to be spherically symmetric. So this term is going to be spherically symmetric. So this term becomes a central potential. So an electron, suppose there are 10 electrons. Each electron has a kinetic energy, it is being attracted to the nucleus, and it is present inside a field created by all the other 9 electrons, an average field created by all the other 9 electrons. It's moving a mean field created by the other 9 electrons. Now that mean field cannot depend upon theta and phi. It depends only upon the radius. How far are you from the nucleus? Okay? So this becomes a central potential or a central Hamiltonian, and it can be solved. However, we have to add another term to this because our original Hamiltonian is given by this. So this term is simply the term that we dropped out. That term is given by E square over 4 pi epsilon naught I less than j 1 over Ri minus Rj. This term is what we left out. Since we added this term artificially, we have to subtract this term as well. So this is our so-called first order correction. Now if we add this term and this term, we will recover the original Hamiltonian. But H naught is easy to solve because it's a central potential. Now what we're going to do is we can treat this additional term as a perturbation, and we can use perturbation theory to find out the effect of this additional term, which represents in fact the interaction. Now notice that this term is the same order of magnitude as this term. Okay, so this is a large term, and you have a difference between two large terms here. It turns out to be a small term. So in perturbation theory, the perturbative Hamiltonian has to be small, and this is what's happening over here. So now you can exploit perturbation theory. You can solve this H naught to find out the eigenfunctions to the 0th order and the energies to the 0th order, and then you can treat this as a perturbative Hamiltonian and find out the energy corrections. So this is the starting point for the whole field of quantum chemistry. In quantum chemistry, if you take a course in quantum chemistry, what happens is you break up the Hamiltonian into a big part and a small part and treat the small part as a perturbation. The big part is easy to solve. Okay. And this is how you find out the eigenfunctions of any atom, or the electronic wave functions of any atom. Remember, beyond helium or beyond hydrogen, it's extremely impossible to solve analytically what the eigenstates are going to be. So you have to resort to approximate methods. Perturbation is an approximation technique. Alright, now what's going to happen is, suppose you have an arrangement of this kind. You have a central potential here. We solve this central potential problem, and then we get as eigenstates wave functions, which are the ground state wave functions. Now, in a central potential for the ith electron, the wave function is simply going to be hydrogen-like because it's a central potential. So you solve the central potential, you will get hydrogen-like wave functions, which are called atomic orbitals. And since H naught does not include any interaction, it does not include any interaction because this is a mean field. Each electron is seeing a field by the nucleus which has been changed by all the other electrons. Okay? So these second and the third terms represents an effective field, right? In effect. So there are Z protons, but there are other electrons. So the effect of both of these terms is that the nuclear charge is being screened. But it's a spherically symmetric field. Now if you solve the Hamiltonian for the spherically symmetric field, atomic orbitals pop out. And each atomic orbital for the ith electron has a radial part, right? Which is denoted by two quantum numbers n and l. And it has an angular part which is characterized by two quantum numbers l and ml, and this depends upon the angles. And this is really a spherical harmonic function, and this is a radial function. So this is when you solve the hydrogen atom, these are what pops out. Now this is for the ith electron. And since there are no interactions, you have n electrons, what you will get is the product of the wave function for the first electron, the second electron, the third electron, and so on. Okay, the zth electron. So the spatial wave function is just going to be a direct product of these atomic orbitals. Alright? However, what appears is, and what's the energy of this state? The energy of this state, the zeroth order energy of this state, is just going to be given by, it's defined by the quantum number n, we all know that. It's given by minus z square over 2n squared m e for 4 pi epsilon naught h bar square, right? It depends upon the quantum number m. This is what comes out of the hydrogen atom when you solve the Schrödinger equation for the hydrogen atom. Okay. So these are the zeroth order energies of these atomic orbitals. Now these energies will change because of the presence of this perturbative Hamiltonian, and you can use perturbation theory to find out how much will be the correction. Now if you would like to talk about, so this is the basics about the electronic part of the Hamiltonian. What we would now like to see is what is meant by the symmetrization postulate. Now, in symmetrization postulate, you must have already seen this in condensed matter physics or in statistical mechanics when we're dealing with indistinguishable particles. So let's talk a little bit about symmetrization postulate. Now the symmetrization postulate suppose I define a variable A, okay, and this variable is basically a 4-tuple, which means it has the 3 parameters r, theta and phi. I'm talking about a particle inside an atom, an electron inside an atom. Now its wave function, the spatial part is defined by r, theta and phi. Right? R, theta and phi are the parameters that describe the wave function. But the electron will also have some spin. So it will have a z component of the spin. Now this A vector is in fact a 4 tuple. It represents these 4 parameters. Now if I have a wave function, that wave function will be parameterized by A. So each particle will be parameterized by r, theta, phi and the spin, because we have to include the spin as well. Now suppose you have 2 electrons. Here I have the x, y and z axis, and I have 2 electrons, one and another electron here too. Remember, these are identical particles. Okay? Any 2 electrons will be identical. Now this electron, its position is defined by, and its spin is defined by the vector A, which is r, theta and phi. And this electron, its position and spin is defined by the vector B. So now you have a 2 particle wave function, psi. The first particle is in a state is parameterized by A, and the second particle is parameterized by B. So each one of these will have 3 spatial coordinates and spin. This will have 3 spatial coordinates and spin. So now you have a 2 particle wave function. Now if you now this particle has been labeled 1, this particle has been labeled 2. So the first position in this ordered pair represents particle number 1, the second position represents particle number 2. However, these labels are totally arbitrary because these are indistinguishable particles. If I swap the 2 electrons, if you close your eyes and I swap the electrons while your eyes are closed, you reopen your eyes, you will not be able to tell whether swapping has taken place or not. So if I apply a parity operator, which is an exchange operator, which exchanges the position of these 2 electrons, I will get a new wave function, psi B A. However, after exchange, what's going to happen is that the new function BA has to be the same as the old function, which means you could have a plus sign here or you could have minus sign here as well, because what is important are the probability and probabilities, and the probabilities are really the modulus square. So as a result of the exchange operation, by swapping the 2 particles just by a parity transformation, the wave function takes up a new form, but this must okay, what's going to happen is that psi BA must be equal to psi AB, or it must be negative, right? So this is what we have here. Okay? So this is the parity operation. The parity operator acts on a state, and you get the original state, okay, with a plus minus sign, and this is equal to psi BA. So this is what the parity operation does. So what the parity operation does is that it swaps B and A, but then the final state that you get is the original state with plus or minus. So the parity operator, this state is an eigenstate of the parity operator with an eigenvalue plus 1 or minus 1. Okay, so this is the parity operation. Now it turns out that there are 2 classes of particles. If you get a plus sign here, then such particles are called bosons. And if you get a minus sign here, then the particles are classified as fermions. Now electrons are fermions, which means that if you exchange the 2 particles, the new wave function has to be negative of the original wave function. Alright. Now let's look at suppose we have two particles and both of them are in the ground state.
inside a helium atom, for example. So you have one electron which is in the 1s state and another electron which is also in the 1s state. Now 1s really means that your particle has an m equals 1, l equals 0 and ml equals 0. So this is the quantum number n, this is the quantum number l, this is the quantum number ml. So 1s electron means you can label that state with the quantum numbers n, l and ml. So this is one electron in the ground state. The other electron is also in the ground state. So the quantum state for the two particles is this state. So you have two electrons in the helium atom. Both of them are in the 1s orbital. Remember, in the ground state, the helium electronic configuration is 1s2, which means both electrons are in the 1s orbital. Now each electron is defined by a quantum state which is totally characterized by the quantum numbers n, l and ml. We need some mechanism of labeling the states, so we can label the states by n, l or ml. Okay? So these are the three quantum numbers that tell us that the electron is in the 1s state. You could also write this as 1s, right? That's fine. You could choose any label you like, but I'm labeling these states by the quantum numbers. So now if you look at this quantum state, this is a spatial, this gives us only telling us about the spatial degree of freedom. Now if I apply the parity operator onto this state, so I apply the parity operator onto this state, which means I swap the two particles. Of course the new state that I get is, so here the first electron is in this state, the second electron is in this state. Now the first electron gets into this state, which happens to be the same as before. So nothing changes. But then, if you have a plus sign here, then the condition for the fermionic character of the electron is not satisfied. However, what we need to consider is that the electron does not only have its spatial coordinate, it has a spin part as well. And the spin part can have even or odd symmetry. Now, what the symmetrization postulate does is that it ensures that the total wave function, which has a space part and a spin part, must obey odd symmetry for fermions. Okay. Now what this means is that if I have a spatial wave function, space, and if I have a spin wave function, this is my overall wave function. When I apply the parity operator onto this overall wave function, and if I'm talking about electrons, which are fermions, then the result should be minus the original wave function. Okay, if I'm talking about fermions, and electrons are fermions. Now what does this mean? Let me give you an example. Let's look at the same example. If I have helium in its ground state, which means the space part is given by this, and the spin part must be given by something, right? To give me an overall wave function. Now, this part, you will notice, if you apply the parity operator only onto this spatial part, it's symmetric. This is what we've seen over here. If the parity operator acts on the space part, you recover the original state. So this is a symmetric wave function. If you were to get a negative sign here, it would be anti-symmetric, but this is a symmetric. You're just swapping the two particles in space. So this part is symmetric. but you would like to have a wave function overall that is antisymmetric. So the only way that can happen is you take this symmetric quantum state and the spin part has to be antisymmetric. Let's see what it means. Let me write down an antisymmetric wave function for the spin. 1 over under root 2 ket alpha ket beta minus ket beta ket alpha, where alpha and beta are the eigenstates of the SZ operator. Alpha represents spin up, beta represents spin down. So this is a spatial part written in white and this is a spin part, and both of these concatenated together give the total quantum state of the two electronic system, of the two electrons. Now if I apply the parity operator onto this state, I swap the position, I swap the two electrons and they are swapped with all of their quantum properties. So what happens is, if I swap the spatial part, the first electron gets this quantum state, the second electron gets this quantum state, and since this is symmetric, it remains the same. Now I'm going to swap the spins as well because the entire quantum character is swapped. So when I swap the spins, this 1 over under 2, by the way, normalizes the quantum state. So alpha and beta are swapped. So the first spin gets a character beta, the second spin gets a character alpha. Quantum mechanics is linear, so I just bring this minus sign here. Here the first spin gets a character alpha, the second spin gets a character beta. Now if you look at this overall wave function, this overall quantum states, this is just the negative of the original. Because this is alpha beta minus beta alpha, just the negative of this. Nothing happens to this. This is a symmetric part and this is an antisymmetric part. So you're multiplying a symmetric part with an antisymmetric part, the overall wave function remains antisymmetric. So if your spatial wave function is symmetric, it dictates what the spin part should be. It must be antisymmetric. This is called the symmetrization postulate. So if you have two electrons, both of them are in the 1s state, both of them are in the 1s atomic orbital, their spins must be in the singlet state. This is called the singlet state. The singlet state is the antisymmetric spin state. It's represented as a singlet. Remember, alpha beta alone would not suffice, because alpha beta alone, after the parity operator, actually gives you beta alpha, and that's neither even nor odd. So you have to have a combination of spins which is either even or odd, and that combination is alpha beta minus beta alpha. So if you have a symmetric spatial wave function, the spin part has to be antisymmetric so that the overall quantum state remains antisymmetric. Alright, so this is an example of the symmetrization postulate. Likewise, so this means if you have a quantum state which is the space part and the space part is symmetric, then the spin part must be antisymmetric. And the antisymmetric spin part is 1 over under root 2 alpha beta minus beta alpha. So this is your overall quantum state. Now, since the space part is symmetric, it dictates what the spin part is going to be. Now, if you were to measure the spin of the two electrons in the 1s ground state, then your wave function, and if you just look at the spin, your wave function is going to collapse. You either get alpha beta or beta alpha, which means that your spins will be oppositely directed. If you perform a measurement on the spins, you will always find them to be opposite in orientation. So this dictates what the relative orientation of the spin is going to be. So if this is your quantum state and you choose to measure the spin, okay? So you choose to measure the spin, you're not looking at the spatial part. Now if you choose to measure, this is your wave function. Now this wave function is going to collapse. So it's going to collapse either into alpha beta with a probability 1/2 or beta alpha with a probability of 1/2. Alpha beta means one spin is up, the other spin is down. So either you get this configuration with 50% probability or you get this configuration with 50% probability. But the point is that both of these spins will be anti-aligned. Okay? So the symmetrization postulate dictates what the spin part is going to be, even though the spin part is totally independent from the spatial part. The constraint on the overall wave function that it has to be antisymmetric under parity exchange, under the parity operation, dictates what the spin part is going to be. If on the other hand, the space part is antisymmetric, right? Space part could also be antisymmetric. This must combine with symmetric spin parts. Now what are the possible symmetric spin parts? The triplet states, right? What are the three triplet states? Alpha beta? So one of them is alpha alpha. See? This part is symmetric under exchange. If you swap the two spins, you'll get alpha alpha, you will recover the original state. Or you could have beta beta. Or you could have 1/√2 alpha beta plus beta alpha. So if you have an antisymmetric spatial wave function, it must combine with one of the three triplets. These three states are the triplet, these are called the triplet spin states. Okay. So you can have either this or this or this. Okay. There are three kinds of triplets. This is even under exchange, this is even under exchange, this is also even under exchange. So there is one kind of singlet, there is one kind of triplet. And sometimes the entire quantum state is also referred to as a singlet or a triplet, deriving the name from only its spin part. So the spin is singlet, the entire quantum state is generally referred to as a singlet state. If the spin part is triplet, the entire quantum state is generally referred to as a triplet. This is the symmetrization postulate. Now if you have this particular kind of combination, which means a triplet state, and if you measure the spins, then both of the spins are going to be parallel to one another. So if you somehow dictate your spatial part to be in the antisymmetric state, it constrains what the spin part is going to do. Both the spins are going to be parallel, either both up, both down, or both down. Alright, so by this inextricable linkage between the spatial part and the spin part through the constraint on the symmetry of the overall wave function, you can control what the relative alignment of the spins is going to be. And this is an important concept for magnetism. Okay, so this is the starting point. Now, how the symmetrization postulate and the electrostatic interaction give rise to the exchange interaction? Let's start our discussion of the helium atom now. So first of all, today we'll all only look at the helium atom in the ground state. This means you have two electrons, both of them are in the 1s orbital. So you have 1s, 1s. Both electrons are in the 1s orbital. Now the overall wave function, overall quantum state is, as we've just written down, is going to be 1, 0, 0, 1, 0, 0. Alright. Now this is the spatial part. Now I'm dropping out this sign. I can drop out this sign and it's superfluous to write it all the time. This is the first electron, the second electron. But you can't really tell which one is the first and which one is the second because these are indistinguishable particles. Okay, so this is the spatial part. Sorry? These are two electrons in an atom. Okay? And then you have a spin part. Since this is symmetric, the two electrons must be in a singlet state. 1 over under root 2 alpha beta minus beta alpha. Okay. So this is the ground state wave function for the two electrons, and it's a 2 electron wave function. It's a 2 electron quantum state. Okay. Now let's write down the Hamiltonian. The Hamiltonian is going to be P1 square over 2m for the first electron. Now plus or minus z e square 4 pi epsilon naught r1. So this is for the first electron. Okay. Z for a helium is equal to 2. There are 2 protons. Now for the second electron, P2 square over 2n minus Z E square over 4 pi epsilon naught R2. Now if the 2 electrons were independent, you wouldn't get anything interesting, but the 2 electrons are talking amongst themselves as well. So there is an electrostatic repulsion between the electrons, and that is denoted by E square over 4 pi epsilon naught R2 minus R1. Okay? So this is the overall Hamiltonian. Now we'll do, since we would like to come up with something analytical, we will use the perturbation theory, but what we would like to do is we'll treat this as the unperturbed Hamiltonian and we'll treat this as the perturbation. Even though we should properly do this kind of manipulation, this is going to give us slightly inaccurate results. Why? Because the perturbative term is of the same order of magnitude as this term, as this term, as this term. Remember that the kinetic energy and the potential energy are of the same order of magnitude for hydrogen atom. And this term is of the same order of magnitude as this term. So this is not really small. We'll get inaccurate results, but they are more illuminating and more interesting. Okay? Because they will bring home the idea of the exchange interaction. So this is the ground state, and this is the central potential. And if you solve this Hamiltonian, the eigenfunctions that come out are these functions. These are the state. This state is an eigenstate of this H naught. And the unperturbed energy, E naught, is going to be given by minus Z ME Z square ME4 over 2n square 4 pi epsilon naught H bar squared. Into 2. Okay, so this is the Hamiltonian for 2 electrons, okay, without the interaction. These are the eigenstates of this Hamiltonian. Now the energy, the unperturbed energy, we know that for a hydrogen atom, an electron in the ground state, the unperturbed energy is minus 13.6 electron volt, right? That minus 13.6 electron volt comes out from here. If you solve the eigenvalue problem, the energies are given by this. So if you have one electron, the energy is given by minus z square m e4 over 2 n square 4 pi epsilon naught h bar square. Okay? So the energy in the ground state, in the nth state of an electron is given by this. Okay, this comes out from solving the Schrödinger equation, which you do in the first quantum mechanics course. Okay. Now here you have two electrons. Each electron has n equals 1. Two electrons, both of them are in the 1s, so each electron has an n equal to 1. So what I've written over here is the same thing, minus z square me4 over 2 4 pi epsilon naught h square 1 over n square for the first electron and 1 over 1 square for the second electron, because you have two electrons. I'm adding up their energies. Okay? Now this turns out to be, all of this is 13.6 electron volts. 13.6 multiplied by 4 multiplied by 2 will give you minus 13.6 into 4 into 2, since you have two electrons. Okay? So this is about minus 108.8 electron volts. So you have two electrons in the helium atom. The energy of those electrons of that system is minus 108 electron volt. Okay? We can draw a diagram for this. You have two electrons. So if I have n1 and n2 representing the quantum numbers for the two electrons, first electron has n of 1, the second electron has n of 1. If both of the electrons have n infinity, which means that the atom is ionized, then we label this energy as 0 electron volts. But this energy we've calculated to be minus 1.8 electron volts, which means that the ionization energy, the double ionization energy of the helium atom is 108.8 electron volt. This much energy is required to have both of the electrons come out of the helium. Okay? So this is the gap between the ionization state, ionized state, doubly ionized state. This represents helium 2 plus. Okay, both of the electrons have gone away. And this represents helium in the ground state. This energy up to 0th order only is minus 108.8 electron volt. Okay. Now we would like to find out the effect of this term, the interaction between the two electrons. Okay. Now this is a non-degenerate state. Okay. Non-degenerate state means it's just one state. Now if you would like to find out the corrections to this energy, the corrections to E naught, how much correction do I need to make because of the presence of this term, I need to use perturbation theory. And the correction to the energy, the first order correction to the energy from perturbation theory is given by the quantum state side in its ground state. Okay, the ground state, because we're finding corrections to the ground state. The expectation value of the perturbative Hamiltonian. Okay, this is what we need to calculate. This is the correction, the first order correction to the energies, the ground state. Now the ground state is given by 1 0 0 1 0 0 crossed with 1 over half alpha beta minus beta alpha. Now H1 as we all know is given by this term. This is H1. This has nothing to do with the spin. It's nothing to do with the spin. So H1 commutes with all the spatial parts, all the spin parts. So in order to calculate E1, we don't need to include the effect of the spin part, because the Hamiltonian has nothing to do with spin. This only has spatial coordinates. So E1 must be calculated in this fashion. Okay, E square over 4 pi epsilon naught R2 minus R1 1 0 0. This will give us the correction to the energy. Okay, we have to calculate this expectation value. First order perturbation theory, time independent, non-degenerate. Okay. Now how do we calculate this? Any idea? How could we calculate this? Remember, this Hamiltonian has spatial coordinates. So we would like to express these quantum states in the position basis. Okay. So we have to convert this into an integral of some kind. We have to express these quantum states in the position basis in terms of r, theta and phi, so that we can calculate this expectation value. This is in a product. So we know from basic quantum mechanics, we all know that any quantum state psi, if we're talking about one dimensions, this can be written as dx, the position ket and bra. This is identity, this acts upon psi. So really we have bx, x ket, x bra psi. Okay. So any quantum state can be written in the position basis in this fashion. Okay. Now this term here, this thing here, is simply called the wave function. It's also called the wave function in the position representation. This is something you learn in basic quantum mechanics courses. So what we would like to do is we would like to express this quantum state in the position basis, just as we do here. This is a one-dimensional example. Here we have a three-dimensional problem to solve. So we would like to express this quantum state. Remember, this is a composite quantum state of two particles. We'd like to represent this quantum state in the position representation. So what we would like to do really is, I don't know if I will be able to finish this off, but let's start this as, I would like to write this quantum state 1 0 0 1 0 0. I represent this as psi symmetric, right? I just compactify it by writing it in this fashion. This is given, now this is a symmetric quantum state. Now what I would like to write this in the position representation. And it's a symmetric state. So I only need to take into account the symmetric basis functions. Because if I have a symmetric state, I take the projection onto the symmetric states only, will I get a non-zero number. If I take the symmetric states and find the projection onto anti-symmetric states and integrate over the entire volume, I will get 0. So I just need to project this state onto the symmetric basis states. So what I would like to do, I would like to write this as an integral d cube r1 d cube r2 1 over under root 2 R1 R2 plus R2 R1 and I integrate over R1 and R2 vectors. These are position vectors, and each of these vectors has an R, theta and phi component. So I write the ket. You see, here first of all I have to write the ket. So I have written down this thing. Now I would like to write the bra. So the bra corresponding to this is 1 over under root 2 R1 R2 plus R2 R1. Now all of this is acting upon the symmetric wave function. So I've just recast this in 3 dimensions. That's all that I've done over here. This 1 over under root 2 is necessary because I want to normalize this. This 1 over under root 2 is necessary because I want to normalize this. So I express my state in this fashion. The other thing is I need 1/2 here, because R1 and R2, both of them are varying over the entire space, and I'm double counting. In order to circumvent that double counting, I need to half this, because suppose R1 is 1 meter, R2 is 2 meter, then I will have R2 is 1 meter and R1 is 2 meter, and both of them are the same. So I have to half this. This is how I express this quantum state in terms of in the position representation. Now what I would like to do, I would like to take up each one of these kets. So this is a ket, and I would like to put it in here. And I would like to form the dual of this. I form the bra of this, and I would like to put it in here. Okay. So if I do all of this, try this on your home, and we'll start on the next lecture with this. If I put all of this in here, okay, you can make certain simplifications here. Remember, when I write this quantum state, the ordering is important. So this represents the first electron, this represents the second electron. The first electron has a position vector R1, the second electron has a position vector R2. Here the first electron has a position vector R2. So ordering is important. In some books they will put a 1 here and a 2 here and a 1 here and a 2 here. But that's just putting in too many symbols. So the ordering, I'm identifying the ordering to be really important here. Now I can also write this in the following fashion. 1/2 d cube R1 d cube R2. I just multiply out these 1/2, put 1/2 here. I can write this as R1 R2, right? I can just compactify this and write this as R1 R2 plus R2 R1. Now what I could do, I could write R1 R2 symmetric, okay, plus R2 R1 symmetric. Okay, so this is my quantum state. I've just written this in a compact notation. Now if you are intelligent and you work hard a little bit, you will notice that this term equals this term, because this is a symmetric wave function. If I interchange R1 and R2, since I have a symmetric wave function, nothing changes. So I can replace this sum by twice of this, and when I replace this sum by twice of this, this 2 goes away. Okay, so I can do, now I can put all of this back in here and I can calculate this E1. I will start off our next lecture by calculating by calculating this, but it will be useful if you could just manipulate this, put these terms into here and see what expression do we get, and then we'll calculate the integral in the next lecture. So what I'm planning to do is I'm planning to do an extra lecture this week, probably on Friday. So Ali will get in touch with you if you have time on Friday. And I've also uploaded a homework. That homework has 1 or 2 computer exercises as well. So I would like you to write a computer program that solves the Landau-Lifshitz-Gilbert equation. I showed you in class the solution for the Bloch equation, the phenomenological Bloch equation, in which the magnetic moment is dissipating with time. So I would like you to do a similar kind of computer exercise for the Landau-Lifshitz-Gilbert equation. And there are 2 or 3 more questions. So I'll see you inshallah on Wednesday.